Whenever you are ready, just start.
I'm Ella Sager.
I'm Mackenzie Manning.
I'm Cadence Foshi, but I go by Race.
And this is our Moon Features Relative Age project.
In the first image, the outline portion is our enhanced image that we decided to do more in-depth research on, which Ella will go over in the next slide. The lighter circle color is craters, or things in the picture we have decided are craters, and the darker purple are domes.
From what we decided that the features on the left, so the first oldest dome, second oldest dome, and third oldest dome, we thought those were some of the oldest features in the picture because of how eroded they look and like low to the ground, not very defined edges. We think those were some of the oldest features. And then on the right, those two craters we thought were younger because they're more defined by looking at the picture. And then the large dome in the middle we thought was more pronounced than the domes on the left. So we think those are younger than the features on the left-hand side of the picture. As I said before, we think the features on the left are older than the features on the right because of erosion and how weathered or eroded down the features look. So
This is image 2. The darker purple again is domes, and the lighter craters. The outline portion is the zoomed in, and we think the big crevice in the middle is real.
okay. So we think that the dome on the right, the large dome, is older than the real in the crater on the left because it's more eroded, as I said earlier. It's lower to the ground, less pronounced. We think the feature on the left is a strait, and we think that's newer because it's more pronounced. There's and the crater under the real, we know that that's younger than the real because of the ejecta rays going over or overlapping the real. As I said before, we think the real is older than the crater because of the ejecta rays overlapping the real, and we think the dome on the right is the oldest feature.
This is image 3. Again, the outline portion is the zoomed in. The darker purple is what we decided were the Mari. The lightest are craters. The pinker one are the highlands, and the regular purple is a real.
Okay, we know for a fact that the Maria is younger than the Lunar Highlands. So we know the oldest feature is the Highlands, the second oldest is the Maria, and then we know that the crater is newer than the real because it's overlapping the real, therefore it's younger. So we know it's the Highlands, the Maria, the real, and then the simple crater. As I said before, we know for a fact that the Lunar Highlands are older than the Maria, and the other features are younger than the Maria.
The highlands were formed by the remains of magma that floated to the surface that became lava, or lava that floated to the surface of magma that became the highlands. The Maria were formed by the melting of and eruption of ballistic magma under the moon's surface. And there's 3 different types of reals. The thinnest which are formed by volcanic activity, and the straight and accurate which were formed by tectonic plates. Simple craters are formed by impacts on the moon's surface, which create a bowl-like shape. Complex craters were formed by larger impactors, and they also had a bowl-like shape, but in the center rebounds upwards. Stuff in the center rebound upwards to the downward pressure of the shock wave, and domes were formed by the cooling of lava that erupted from vents in the lunar crust. And that is everything.
Okay. Did you have the asteroid presentation also?
I'm sorry, what did you say?
Did you
No.
also have the asteroid presentation?
We missed that part. I thought we did. I don't remember doing them at the same time. That's my fault.
Oh, that's fine. No, it's okay.
We're-
It's okay.
Yeah, we're about halfway through the asteroids.
Okay, no problem. No problem. No problem at all. Just wanted to make sure we're on the same page. Okay, great. Very nice. Very good. Let's see. Let's so just a couple of general comments. And this isn't so much a big deal right now because we're doing this virtually and I'm sitting right here in front of my screen, and anybody else who might be watching this virtually is sitting right in front of their screen also. But for future reference, if say you're presenting in your classroom, maybe to your peers or in a larger room somewhere, and you're displaying on a screen, your color choices here don't have a whole lot of contrast. Like say black and white and red or black and white and yellow, you know what I mean? So if there's somebody who's sitting in the back of a room looking at this, they may have a hard time figuring things out, particularly when you have the different circles, when you have the circles around different features. So something to keep in mind. And from another standpoint, you know, there are people with various degrees of color blindness. So some things may not stand out. And just another aside, there's actually websites you can go to where you can like upload a PowerPoint slide that has a color scheme that you're using, and it'll like tell you, like, yeah, that's good. Or you might want to consider changing this but those are very specific for, you know, different types of color blindness. But for our purposes, I wouldn't worry about that right now. Anyway, and also a general comment is the font is cool, but that also could be difficult to read from a distance. So just something else to keep in mind for the future. Let's go back to the first image where you had your annotations. Go back up to the one before that.
Ooh, wait. Okay.
Okay, yeah, you can leave it like this, that's fine. Okay, so this is a little bit of a tricky picture, and I kind of did that on purpose. So every circular feature you see in this picture is an impact crater. But I do like, or let me ask you. So I did like how you talked about, you know, your reasoning for ages, for relative ages, right? How they look more eroded, like you can't really tell what it is anymore, but you can kind of tell what it is. That's great. That's good thinking. How did you decide what was a crater versus what was a dome?
Well, we had a very long discussion about this because it was really hard to tell. But we were trying to look at where the light hit, but that gave us some problems too. So we kind of just decided you know, some of these features look like domes, some don't. So we just differentiated that way.
Did you look at any, did you see any other pictures before this one? Did you see any other pictures that did have, where they were like, these are domes, that you compared it to?
We didn't compare it.
We might have looked at a couple, but I'm not sure. I don't remember.
So you're just kind of going off the description of domes in the text?
I think so, probably.
Okay, that's fair. Yeah. So what piece of information would have been useful to have with this picture that may have helped you out with that dome versus crater?
If it was in a Maria or in the Highlands,
Okay, why that?
well, because the Highlands have more domes. Well, they have domes in them and craters.
Okay,
And then Maria's flatter and has more impact than uprising elevation.
okay, okay, okay. Any other information that could have been useful?
We probably should have looked up more reference pictures to determine the difference between domes and craters on the moon.
Okay. Yeah, you could have done that. That could have been something that you could have done. Hindsight's 2020, right? So the one thing that would have been really useful, and you've alluded to this already, is if you would have known what direction the sunlight was coming from. But as you said, in some cases that doesn't help. It's kind of difficult, particularly for craters that are very, very shallow, and they're shallow because they've been filled in over time with dirt and dust from impacts farther away, throwing that stuff into the crater and filling it up. So sometimes they're almost completely erased. You really can't tell anymore. So yeah, this is a tough one to analyze. So I will say, so this is in Mari. This is on a Mari patch. The brighter areas you see are stuff that's been dug up from an impact and brought to the surface. Did you happen to notice? I don't know if you can you? You probably can't see my cursor, can you? Okay, take a look there at that at your square, your dotted square, up towards the top, kind of just below that first longer dash, that longer dashed line. It's kind of in the middle to the right, the middle right, kind of. Do you see something kind of just below that? It looks a little different.
Can you describe where it is again?
Okay. Yeah, move your cursor. Okay, move your cursor right just to the below and left of your cursor. Right there, that thing. Do you know what that is? I'm guessing you don't, or you would have called it out.
It just looks like any other feature. I don't know.
Like maybe a boulder or a rock, something like that. So that actually is the Apollo 12 lander.
Oh.
That is the piece of the lander that stayed behind after the astronauts lifted off and went back into lunar orbit to come back home. And so those linear lines you see going away from it, and so they go away from it to the right, to around to that other crater to the right, and they kind of go off to the left and go around that crater and come back down to the bottom of that crater. Those are astronaut footprints. That's where they disturbed the regolith, okay, what we might call dirt, on the surface of the moon as they were walking around. There's also trails there from, they had this little cart that they carried equipment in, tools behind them. So it's kind of that, it's kind of the cart trails and their footprints at the same time. And the reason they came all the way around to the other side of the crater here is because a robotic spacecraft landed there a few years before, in 1966 or 67, I don't remember. It's called Surveyor 6. and they went over, took a piece of it off, took a piece off the spacecraft, and they brought it back to Earth with them. And so then scientists did some studies on what the effects of being exposed to solar radiation for a couple of years did to that metal. So that's kind of cool. Yeah, so Zamare, it's all impact craters, various sizes, various ages, but they're all simple impact craters. They're all simple bowl shape. Okay. Go to the next image, image 2. Oh, okay, just real quick. Yeah, that's fine, you can stop there. But the previous slide where you had the bullets talking about stuff, summarizing things. In general, you don't want to have slides that are just full of text. Anything if you want to make sure you have a slide like that, as a way to like remind you to talk about something, that's fine. But I would find ways to have them have as few text as possible, and maybe have images to replace them. Maybe they're different than what you have been using, but would complement, what you're talking about. Okay. Okay, so again, in this image, these are all craters. This is probably an even tougher image to look at and analyze because the sun angle on this is incredibly high. The sun was very high over this particular part of the surface when this image was taken by a spacecraft. There's almost no shadows at all. So if you look at this under different lighting, it looks completely different. So yeah, I mean, in your in that box there, right on the very left edge of it, it looks like a fairly large something, maybe a crater, but it's not circular or doesn't appear circular in any way, and that's because of lighting, the lighting effects. But that is, so the big circle there, that is part of a rill. So that's a depression into the ground. It's part of a sinuous rill that was formed by lava flowing. Usually what happens is if the lava is flowing under the surface in what's called a lava tube, and then after the lava runs out, the eruption ends and the lava drains out, there's just this cavity left. And over time, and after if enough impacts, small impacts hit the top or near it, or a big one hits near it, that will cause that roof to collapse. And so then you're left with just this channel that used to be filled with lava. And if you get really close into these, and look really close into here, you can see a lot just littered with boulders and rocks on the floor of it. Okay. And to go to the number 3, just want to point something out there real quick. Okay, so in this image, just above your the rectangle, there's that crater sitting there on that mountain, on that highland right there. Just above that, there's that little hook, little bend in that rill. Do you see what I'm talking about?
Right here?
Right, yeah, just right, yeah, right there. That little elbow right there. That little area was in the previous image. So that previous image is just a zoomed in shot of that. This image was taken by the Lunar Orbiter spacecraft from the mid-1960s. The previous one was taken by the Lunar Reconnaissance Orbiter that's still orbiting the moon and taking images. So it's a different spacecraft, 40 years apart, almost 50 years apart, but looking at the same area. So this is one of my favorite images because there's, as you've pointed out, there's so much geology here. And you did a great job of talking about the relative ages of these features and explaining why. So that was really good. Well done on that. And then finally, let's just take a look at that slide that says, oh, one thing I'll mention. Just to the right of that elbow, that bend, there's a little cluster of craters there. And then just kind of above those a little bit, that's where the Apollo 15 astronauts landed. And they actually took a rover up to the rill and took some pictures looking down into it. It's big, it's huge, it's like a mile across. It's pretty big. Okay. I want to go to the slide where we have the, like, where you talk about the formation of features. Okay, yeah. So again, just in general, this is a slide with a lot of text, but that's okay. So just a few factual things. So what you have here is correct in general, but with some slight tweaks. So the highlands, yes, that was from magma that solidified and formed the magma, the original, or the surface, the original crust of the moon. But it wasn't rock that floated, it was the minerals that then solidified to make that rock. So a little different, but it's actually it's an important distinction. So this is the time when the moon was completely molten, and you had lighter elements and minerals coming to the surface, and you had the heavier, denser ones going down towards the core. And then as it cooled, it became the highlands, became the bright stuff. Mare, yes. It was under the surface. There was the late heavy bombardment period that really pelted the moon, weakened the crust in places, and then later that hot magma, basaltic magma under the surface was buoyant, and it'll push through the crust, then spill out and fill in those craters. So yeah, sinuous rios are volcanic, and the straight and arcuate are tectonic. What's the difference between tectonic and plate tectonics?
Well, I know tectonic plates, like on Earth, it's these giant plates that kind of move against each other.
Mhm.
Tectonic.
Earthquakes or shockwaves.
Okay, so the difference is plate tectonics is a type of tectonics. So tectonics is a general term that refers to the crust of a surface moving. So like you said, the Earth's crust is broken up in these plates that move in different directions relative to each other. Okay. Now, the surface of an object or a planet or a moon can move, that can experience tectonics, but not be broken up into plates. So plate tectonics is a very, very specific process that we really only have good evidence for on the Earth. We might think we're seeing something on Venus, that there may have been plate tectonics on Venus, but it may just be very regional, very local, and it has ceased by now. There's been some evidence that maybe Mars may have had some plate movement, but not real sure there either. So yeah, so straight and arcuates are formed from the fact that the moon's surface, even though it's not broken up into plates, it has moved and shifted. Some of it in part of the fact that as it cooled over time, it shrunk. And because there are no plates and there's nowhere for that crust to go, it breaks. As other places where it breaks, something somewhere else has to give, and so it splits. But again, not necessarily because of plates. So, okay, simple crater. It's that simple. Complex craters aren't really bowl shaped. They tend to have a fairly flat floor compared to a simple crater. But yes, you will see things like the central peaks in an impact crater and complex craters, and you'll see in really big ones, the walls have like a terraced look to them because they collapse under gravity. And really big complex craters, where we start calling them basins, kind of start looking like targets, like bullseyes. Orientale basin on the moon is a good example of that. But it doesn't have a central peak. Very big. All right. Okay, that's what I got for you. Otherwise, very good. Very good job. Great start. So go ahead and stop recording.